Good evening. I am Professor Shalini Sahay, Assistant Professor in EC Department, SIRT Bhopal. Today, in this lecture, I am going to discuss some more theory about the transmission line. Here, we will discuss about transmission line as in half and quarter wave lines. The relationship of the input impedance at the input of the half-wave transmission line with its terminating impedance is got by letting where we will assume the length of the transmission line as lambda by 2, where lambda is the wavelength. Now we will put this equation in the input impedance equation of the transmission line. Here Z input is equals to ZL into W. The relationship of the input impedance at the input of quarter wave transmission line with its terminating impedance is got by letting L is equals to lambda by 2 in the impedance equation. Here the input impedance is equal to under root of Z input into Z output into W. Effect of the lossy line on voltage and current waves. The effect of resistance in a transmission line is to continuously reduce the amplitude of both incident and reflected voltage and current waves. Now we'll discuss about the skin effect. As frequency increases, depth of penetration into adjacent conductive surfaces decreases for boundary currents associated with the electromagnetic waves. This results in the confinement of the voltage and current waves at the boundary of the transmission line, thus making the transmission more lossy. Now we will relate the skin depth is given by this following equation. Here F is the frequency, M is the permeability, and G is the conductivity, F is the frequency, and it is under root. Now, main application of the Smith transmission line is the Smith chart. With the Smith chart, we can analyze the complex transmission line problems, and the use of formulae becomes increasingly difficult and inconvenient. An indispensable graphical method of solution is use of the Smith chart. Components of a Smith chart. Horizontal line. The horizontal line running through the center of the Smith chart represents either the resistive or the conductive component. Zero resistance or conductance is located on the left end, and infinite resistance or conductance is located on the right end of the line. Circles of a constant resistance and conductance. Circles of constant resistance are drawn on the Smith chart tangent to the right hand side of the chart and its intersection with the center line. These circles of a constant resistance are used to locate complex impedances and to assist in obtaining solutions to problems involving the Smith chart. Now, the lines of constant reactance. Lines of constant reactance are shown on the Smith chart with the curves that start from a given reactance value on the outer circle end and at the right hand side of the center line. Now, the solution to microwave problems using Smith chart. The type of problems for which the Smith charts are used include the following. First, plotting a complex impedance on the Smith chart. Finding the voltage standing wave ratio for a given load. Finding the admittance for a given Impedance. As we know that admittance is the inversely proportional to the impedance. Now, finding the input impedance of a transmission line terminated in a short or open. Finding the input impedance at any distance from a load ZL. Locating the first maximum and minimum from any load. Now, plotting a complex impedance on a Smith chart. To locate a complex impedance, Z is equals to R plus minus JX, or admittance Y is equals to plus minus JB on a Smith chart by normalizing the real and imaginary part of the complex impedance. Locating the values of the normalized real term on the horizontal line scale locates the resistance circle. Locating the normalized value of the imaginary term on the outer circle locates the curve of a constant reactance. The intersection of the circle and the curve locates the complex impedance on the Smith chart. Now, finding the voltage standing wave ratio for a given load. First, we normalize the load and plot its location on the Smith chart. Then we'll draw a circle with a radius equal to the distance between the 1.0 point and the location of the normalized load and the center of the Smith chart as the center. The intersection of the right-hand side of the circle with the horizontal resistance line locates the value of a voltage standing wave ratio. Now, finding the input impedance at any distance from the load. The load impedance is first normalized and it is located on the Smith chart. Then, the voltage standing wave ratio circle is drawn for the load. A line is drawn from the 1.0 point through the load to the outer wavelength scale. To locate the input impedance on a Smith chart of the transmission line at any given distance from the load. Advance in clockwise direction from the located point a distance in wavelength equal to the distance to the new location on the transmission line. Now the power loss. Return power loss. When an electromagnetic wave travels down a transmission line and encounters a mismatched load or a discontinuity in the line, part of the incident power is reflected back down the line. The return loss is termed to be as power loss and it is given by 10 log 10 Pi upon PR, or P return is equals to 20 log 10 1 upon VSWR. Mismatch power loss. The term mismatch loss is to describe the loss caused by the reflection due to a mismatched line, and it is defined by the formula 10 log 10 Pi upon Pi minus PR, where Pi is the incident power and PR is the reflected power. Thank you.